Hello everyone, we will continue with our lecture series on this optimal control guidance and estimation course. And so far we have seen calculus of variations approach which leads to this 2-point boundary value problem, followed by this LQR which is a subset of that, and then the little bit extension of that in the framework of SDRE and theta d. Okay. And then last couple of lectures we have also seen what is that this dynamic programming approach where it leads to these Hedge-Bezier equations. However, the Hedge equation is nonlinear partial differential equation and all that. So, that lands up with this curse of dimensionality. The first approach leads to curse of complexity, the second approach leads to curse of dimensionality really. But anyway, so there are techniques, evolving techniques and all that which tries to avoid those problems in a limited sense at least. And one of that happens to be approximate dynamic programming, which I have already seen there. Okay. And similarly, we will slowly what I am telling is we are going towards the so called real time optimal control. That means the solution techniques are so powerful that the solution is available very quickly actually. So, that means you can think of using these algorithms really online. So, this one of these technique happens to be this model predictive static programming, which I am going to talk in this lecture as well as next lecture. And we will see some application of this particular technique in the framework of optimal guidance of aerospace vehicles. Okay. So, essentially if you know any guidance problem is a trajectory optimization problem. That means it can be, ideally it should be formulated as an optimal control problem, but because of this curse of dimensionality or curse of complexity, these are typically never used online. However, as I told, there are several methods evolving which tries to kind of overcome that, and one of that happens to be this model predictive static programming. So, let us see what it is. So, outline of this lecture will be something like this. First is motivation, why we do that, and then some mathematical details of this particular design, and then I will take you through a little bit intensive way this re-entry guidance of a reusable launch vehicle using this MPSP technique, and ultimately I will give you some references to follow it up as well. Alright, so let us get going. The first is motivation, and let us see what motivations are there for this particular technique. The very first thing that comes to mind is high computational efficiency. That means what you are looking for is some sort of real time online solution. The second thing what you are looking here is terminal conditions should be met as hard constraints, and especially in missile guidance problems this essentially leads to high terminal accuracy. That means if you are working on a missile guidance problem, the very first thing that you want is to go towards the target as close as possible, and in that sense hard constraints are typically much better actually. I will take you through some examples in next class and all that actually. Alright, so that is the next thing, okay, and especially it is not necessarily only missile guidance. In any aerospace guidance or ground vehicle guidance, underwater guidance, anything that you think about, the ultimate aim is when T goes to TF or final time goes to current time goes to final time, you want certain objectives to be met actually. In other words, your position vector should be very close to the target position vector, and your velocity angles especially should be in some particular desirable values and all that actually. Those things can also be met actually that way. So, it can be essentially used for any aerospace vehicle, and especially very particular it can be for missile guidance as well. So, the next one that you are looking for is no approximation of system dynamics. That means as we saw that in the adaptive critique techniques and all, we do not want to kind of linearize the system dynamics or quasi-linearize and things like that, and then talk about lot of analysis which essentially leads to some sort of a closed form or semi-closed form solution. However, the very fact is we have actually started with linearizing the system dynamics, which you do not want to do. Okay. The next one is on the way minimum control usage is also our objective. Of course, that should not be compromising the output accuracy at the final time. Okay. So, without compromising on the output accuracy at the final time, what you really want is a path from a given initial condition, which will take actually minimum control and lead to extremely high accuracy, and we really want a very highly computational efficient method, which will essentially lead to real time online solution actually. So, that is the type of motivation that we are looking for here. Alright, so this model predictive static programming, obviously you can see that partly the very name suggests model predictive. The philosophy is partly borrowed from model predictive control. Okay. So, this model predictive control is something like output dynamics replaces the state dynamics in a 2-point boundary value problem, and that is what the features some of the features of this MPSP technique is actually relies on that part. What about the other side of the story? It is also inspired from the philosophy of approximate dynamic programming, and both of the techniques you have seen so far. So, I hope you are able to connect what I am talking here actually. So, essentially what's the approximate dynamic programming? It is essentially a discrete formulation that avoids the HJV equation in a way. So, here we also talk about a discrete time framework in this particular design, where the particular steps and things like that are inspired from model predictive control side actually. And those of you who want to refer the details part of it and all, you can actually see this reference. This is the first publication that we published in about 2009 in a journal actually. Okay, so you can see that, and I will also list out a few more journal papers and conference papers, things like that at the end of this lecture as well as next lecture actually. Alright, so let us get on with the mathematical details part of it now. We will slowly go through the steps and try to understand what is really happening here actually. Okay. The very first thing is, as I told, it is also inspired from discrete system dynamics and all that. So, very first thing to do here is we have a system dynamics in this form. Remember, this is a complete nonlinear form, and then there is a output which is also a nonlinear function of x actually. Sorry. Okay. Okay. So, this is actually a nonlinear system dynamics and also kind of a nonlinear output, and also remember that this output that I am talking here is actually the desirable output. It is not really the sensor output actually. Okay. So, both the things are discretized. Okay. Typically it is done through this the system dynamics discretization is typically done through this Euler integration actually. Okay. So, what is the objective? Objective is as we go along, that means k varies from actually this if you interpret that in the form of time domain, this is 1 k varies from 1, 2, 3, 4 like that, and ultimately you have this n, and just before that is n minus 1, and remember control typically acts up to n minus 1, where state evolves up to time step n actually. So, what you are looking here is at time step n, okay, we have this this objective to be met is this yn, which is nothing but h of x n, okay, should go towards a particular desirable value yn star. Okay. And of course, as I mentioned before, with additional some optimal objectives and all, we will assume on the way actually. Okay. So, this is the particular problem when you when the state starts evolving at the final point n, okay, you have a x n, okay. Okay. All right. At the final point n, we have this x n, and this x n, if you evaluate h of x n, then we will get y n, and this y n should actually go to certain y n star actually. Okay. That's our objective basically. Okay. All right. So, what is the philosophy here? Obviously, we start with some sort of a guess history. That is typically with respect to this is a typical way of solving optimal control problems. We start with a control guess history and we have initial condition. So, we start propagating the system dynamics, and ultimately when we reach there we arrive at some sort of yn value, but obviously that is not close to yn star because the control that we have applied is actually a guess history control. Okay. So, there is an error there, and so the objective here is how do we adjust these guess value of the control history, so that after the update the trajectory will actually lead to that particular xn, which will using which if you evaluate yn, it will be closer to yn star actually. Okay. So, that is the objective here. So, mathematically speaking, we can define some sort of a error okay, delta yn. Okay, this delta yn is nothing but yn minus yn star, and that should go to 0. Okay. Remember, yn should go to yn star. So, obviously, the difference should go to 0. Okay. So, what is the philosophy? First, we have to guess the control history and then simulate the system dynamics from the initial condition that we are interested in. Okay. Then, we have to compute the error in the output, okay, at the final time, and we have to utilize this error information to update the control history optimally. Okay. Then, obviously, we have to repeat this iteration until convergence. Okay. And somebody can see that the steps, if you see it little carefully, this is very close to what we have seen in shooting method actually in a way. Okay. Then obviously, somebody can ask what is the beauty here. The whole beauty here is the update happens, iterate the control history until convergence. What you see in the last step, this iteration happens very fast actually. Okay. So, why it happens and all that I will tell you as we go along actually. Alright, so let us start analyzing this. See, as I told, we started with a guess history of the control, but that leads to this error in output. Okay, of the output at final time. So, now we want to analyze this error, okay, and tell how much the error we have done in the control everywhere actually. Remember, we have a control here in this time history. If you go back, you have a control u1 here, you have u2 here, you have u3 here, and things like that actually. Okay, all the way up to un minus 1. The thing is, these values are erroneous. So, we want to update it. So, obviously, we want to update u1, u2, everything. Okay, so that the updated control history will take us to the desirable value. Okay. Alright, so we want to analyze first, okay, how much error we made and what is the effect of that error in this delta yn actually. Okay, how much error we made in the control everywhere, all the time steps, and how much effect it had in this particular delta yn actually. Okay. So, here we introduce this small error approximation. Obviously, that demands that you start with a reasonably good guess basically. It did not be very good, but ultimately it turns out that it is not that sensitive actually. You can start with a large error as well, but theoretically speaking it demands that, okay, this delta yn is approximated like a dyn actually. So, that is a small error approximation, and using this small error approximation, okay, what you do here is the delta yn by delta xn into dxn actually. Okay. That means, this dyn, what you see, we analyze that where does it come from actually, because ultimately remember y is a function of x. Okay. So, if there is an error in y, it has to come through the error in x, it cannot escape from that actually. Okay. So, we assume that is what it is. Okay. And also assume that we are not starting from really, this is actually, it can be applied from any time. So, what we are telling here is our, okay, let me, okay, we start with not really 1 every time. Suppose we are operating at time point, time step 3, then that becomes our initial time. That means, we start operating from any k actually really. Okay. So, that is what we are doing here. So, we want to analyze backwards up to time step k basically. But anyway, so coming back, this was an error delta yn. Okay. So, this is this small error approximation dyn, and this calculus simply tells us that this dyn has to happen because of dxn, and this is the relationship actually. Okay. Now, the question here is what is this dxn? Okay. You have this time step n, and then there is n minus 1 actually. Okay. There was a problem in xn. Okay. However, this xn, if you see the system dynamics, system dynamics tells us that xk plus 1 is a function of fk, xk, uk basically. Okay. So, obviously, if there is an error in xn, then there is some error in xn minus 1 and un minus 1 actually. So, that means, xn minus 1 and n minus 1, okay, well, okay, xn minus 1 and un minus 1 both have an effect towards xn actually. Okay. So, that is why any amount of error that I make in xn, okay, there is certainly some error in xn minus 1 and un minus 1 both actually. Okay. So, that is why I want to expand this dxn, okay, in the variables dxn minus 1 and dun minus 1 actually. Okay. And remember, this is the instead of going back again, what we have here is k plus 1 is actually f of xk uk. Okay. So, obviously, xn, okay, xn happens to be a function of xn minus 1 and un minus 1 actually. Okay. So, if you see this, then obviously dxn, if you see that from this expression you can relate to this dxn, okay, this particular thing you can find out, and then you can tell, okay, this should be related to something like dxn, and then there is something like dun actually. Okay. So, this is what we want to do. Okay. So, we do not want to touch that we keep it as it is, but dxn I want to expand it backwards, okay, and then I want to write it as something like this, okay, df(n minus 1 by del f n minus 1 by del x n minus 1 into dx n minus 1 plus del f n minus 1 by del u n minus 1 into du n minus 1. Okay. Now, here what you see here is this control variables are all decision variables. That means, if you made some error there, then there is a direct chance of correcting that actually. Okay. So, this does not come from anywhere, because we took a wrong decision, that is why this du n minus 1 is coming actually. However, what about dxn minus 1? Again, going back to that, anytime the state evolves because of the previous state and the previous control actually. Okay. So, again you see that, okay, dxn minus 1 I can expand it in the form of dxn minus 2 and dun minus 2 actually. Okay. This particular thing, what you see dx minus 1 is expanded in the form of dxn minus 2 and dun minus 2 actually. Okay. So, dun minus 1 we keep as it is, that we do not want to change actually. Okay. This one is kept as it is actually. Now, what happens is you continue this exercise okay, until the final, until the initial time, and as I told here in this problem, okay, we interpret the initial time as up to k actually. So, I start with n, then n minus 1, then n minus 2, and I keep on continuing this way, okay, and here I will end up with this time step tk, okay, this represents tk. That is where my problem starts actually. Okay. So, I will continue up to this time step k basically. Okay. So, I will do that, and then I can see that the entire expression will lead to something like this actually. Okay. There is first there will be some sort of error in the initial condition, okay, dxk, that is my current time condition of the state. So, that is my error in the initial condition. And then there is a bunch of expressions which will tell us that, okay, there is an error in duk, the next term will tell us there is an error in duk plus 1 and things like that actually. This will continue up to this du n minus 1 actually. Okay. And some of you can now see that there is some degree of kind of inspiration from approximate dynamic programming. That is what this sensitivity analysis part, what you are talking here is kind of borrowed from that side actually. Alright, what next actually? We have done that, but here we observe that there cannot be any initial condition error, because we assume that the initial condition is known to us actually. That is where we want the solution anyway. So, this goes to 0. Okay. So, ultimately what it leads to is something like this actually. So, this dy n what is evaluated as delta y n is can be expressed as bk times duk plus bk plus 1 times duk plus 1 all the way up to bn minus 1 times dun minus 1. Now, these matrices what you see here I redefined as bk plus 1 and all that here okay, somebody can argue that, okay, what is happening here? It is actually, if you see the first thing, then it is actually multiplication of 2 matrices. The very previous one will be a multiplication of 3 matrices, and it keeps on piling on actually. Okay, that means your number of matrices computation of for computing the sensitivity matrices is essentially large actually in a way. So, how can that computational efficiency be retained? Now, if you look at it slightly closely, it turns out that these matrices actually can be computed recursively. Okay, so, this recursive computation actually is one of the key features why is this computational efficient actually. I will tell you there are other reasons as well actually. And also notice that the dimension of this equation here, okay, what you see here is dimension of yn. It has nothing to do with dimension of state actually really. Okay, and typically this dimension of y happens to be much lesser than the dimension of the state. That means ultimately the number of equations that you are talking here is dictated by how many outputs you want to control at the final time really. Okay. So, that actually helps and that gives us another reason why it is computationally efficient actually. Okay. Now, also notice a big thing here, okay, that this particular relationship what you are getting here is actually an algebraic constraint. Okay. There is no differential equation involved and all that here. That is probably the biggest reason why this is computationally more efficient actually. That means, somehow there is a hope that we can actually formulate a static optimization problem actually. That is why this name model predictive static programming is given. By the way, as I have told before, programming stands for optimization actually. So, model predictive static optimization you can think about that actually. Okay. Anyway, coming back, this is the constraint equation that we got. What it tells is, okay, we made these much errors, okay, this duk plus 1 and all that. So, this much errors we made and hence we ended up with this dyn because these are the sensitivity matrices associated with them. Bk is a sensitivity of duk, okay, with respect to dyn like that actually. Okay. Alright, so this is what it is and we will see how these matrices can be computed recursively. This is the relationship that you can see about. If you talk about any bk tilde, okay, this k tilde is actually a dynamic variable like this, then any bk tilde can be expressed like this. Okay. So, if you observe little closely, first we can probably define this b n minus 1 0 as something like the coefficient that multiplies everywhere. Okay. And then we operate on this kind of iteration actually. Bk 0 is bk bk tilde is bk tilde plus 1. That is essentially it is a backward recursion actually. So, this one multiply by that actually. Okay. Whatever additional term you are getting here, we will multiply with that actually. Okay. Ultimately, after computing all these bk zeros, all that we do is we multiply all this bk tilde by bk tilde 0 into del fk by del uk. That means, what you see del fk by del uk, we take it out, separate it out, and the in between terms that remains, we just start kind of getting recursively. Ultimately, we just multiply one shot actually. Okay, so that is the way of recursive computation of the sensitivity matrices actually. Okay. Now, what about this? Now, what you see here, this constraint equation is a small dimensional algebraic constraint equation, that is clear here, but also remember how many free variables we have. This number of free variables depends on the dimension of the control variable multiplied by the number of time steps available. Okay. So, that means there are so many freedoms out here, okay, unless you assume that you are at the very final time and things like that, forget that. You can assume that there are enough time steps here available. So, that means we have lot of freedom and what we want is actually a less number of constraints. That means, it is severely under constraint equation actually. So, when you have something like an under constraint equation, there is a scope of optimizing actually. So, that that essentially leads us to this static optimization ideas actually. So, what you do here is not only you want to satisfy this constraint, but you also want to think about minimizing the control history this way. So, why this term here? This is actually the updated control. Okay. So, the control history will be updated that way. You have this previous value okay, or the guess value of the control to begin with, or the previous value, and this is what the correction you want. So, this is what the updated control value will be, and this one transpose times r into duk and r into u. That's essentially what you are telling is u transpose r u sort of thing. Okay. So, essentially you are telling that okay, I want to have some sort of a control minimizing solution actually. And also remember, there are enough freedoms out here, a little bit more freedom out here, but in some particular problems, it may so happen that you will want a solution which will actually minimize duks, not uk in general actually. Okay. Why? Because if you really, I will see that next example and all, if your control history that you want has to be bounded between some maximum minimum value, you will typically like to operate in the middle segment actually, that is trivially typically non-zero basically. Okay. So, in those situations you would like to have this DUK transpose R DUK instead of UK transpose R UK sort of thing. But anyway, just to maintain generality, we will assume that it is a control minimizing solution. So, we will take this cost function subject to this constraint, okay, whatever constraint you have taken, I have derived already basically. Now, we can clearly see that it is actually nothing but a static optimization problem actually. Okay. So, we can follow the very standard formulas, standard rules, logics, whatever we have studied before for static optimization. And then the procedure tells that we have to first construct some sort of a augmented cost function, okay. And this augmented cost function is something like this. We have the original cost function plus lambda transpose this entire equation, okay, minus dy and sort of thing. Okay. Once you have that, this is actually a problem for jk bar. The free variables here is dus and lambdas as well actually. So, we have to take derivatives of with respect to both actually. So, we take a derivative with respect to duk tilde first, okay. So, that essentially leads to something like this, and then we have this second equation del jk bar by del lambda equal 0, which talks about something like this, okay. Now, these two equations needs to be solved together to get your control history, get our control history update actually, okay. Now, what you observe here again, this because this is a static equation that we started with, okay, the co-state variable that you require here is also static, okay. That means, just a constant vector that we need actually, and that is probably the biggest reason why it is computationally efficient. In other words, utilizing a single vector lambda will be able to update the entire control history, okay, which is a major departure from this 2-point boundary value problem solutions ideas actually. Anyway, coming back, these are the two equations that we want to solve and essentially eliminate lambda. So, how do you do that? First you solve this in terms of lambda, then substitute here, solve for lambda and go back actually. That is what it is done here. You solve these values in terms of lambda, then you go back to the constraint equation, put the value expressions there and solve for lambda. Okay. Once you solve for lambda, you can again go back and put the lambda values here and get the solution that you require actually. So, essentially it will tell us that lambda can be solved something like this, where a lambda, okay, is defined like this and b lambda defined like that. Once lambda is known, our duk histories are all known actually. Okay. Again I emphasize or I repeat that with a single co-state variable, okay, you will be able to compute all the necessary corrections for control variables at all the grid points actually. Okay. Alright, so this is how it is. Also closely you can, if you notice this, if you see this a lambda and b lambda are typically functions of only this the sensitivity matrices largely, okay, and RK inverse and all the RKs are typically selected as part of the cost function, and this UK0 is your previous solution, that means previous either guess history or the previous iteration value actually. So, knowing the previous values, okay, and knowing the sensitivity matrices, we can very quickly compute lambda, okay. Remember, sensitivity matrices can be computed recursively. So, using that you can compute lambda, and once you compute lambda, your control history updates are all known actually, okay. So, this is why it is why it is computationally efficient actually. So, finally, the control update can be written something like this, okay, and your lambda is given like that actually. Also, at this point of time, somebody can argue that, okay, in our own observation, most of the time this entire method converges very rapidly also, okay. We just need about about 4-5 iterations at the maximum for getting some good solutions actually, okay. However, you can also think that, okay, even if that is not allowable, suppose my time sequence is very large and then even one iteration takes long time and things like, I am not sure how many iterations it will take and things like that. Then it will, you can think about doing, incorporating this idea of iteration unfolding. That means, it is very simple. It's all that it tells is, okay, I start with k, I have k plus 1 and I have to go all the way up to n minus 1 anyway, okay. So, what I will do is, I will operate based on a fixed number of iterations, okay. So, suppose I operate based on something like I will not wait until it converts, but I will operate based on let us say 5 iterations only, and my computation will show that I can actually do the 5 iterations in the available time window actually. So, every time I will either operate on the fixed number of iteration, or I can change that as well. Okay, I can operate 5 iteration here, 5 iteration there, and things like that. Or as you remember, as you note that when you go closer and closer, okay, your time available becomes shorter and shorter. That means number of time grids actually. Okay, so number of time grids become smaller and smaller here. Okay, so then you can think of okay, wait, I can actually do more number of iterations necessary. I can probably do 8 iterations there actually. But these number 5, 8 and all that will be priori fixed depending on your problem actually, and depending on the computational power and real time algorithm that you use and things like that actually. So, nobody forbids from doing that, but however, my observation, my comment here is in many of the problems that we have solved, it actually takes about 4 5 iterations only to converge anyway. So, the entire algorithm can be represented like this. It's very close to a kind of sorting method if you think about. You start with some sort of a guess control history, propagate the system dynamics, compute the output, check for convergence, and largely when I talk about convergence, I talk about output convergence, whether yn has gone to yn star actually. And also remember, when yn goes to yn star, or at the same time it turns out that j also goes to some sort of j also, I mean the cost function also tries kind of goes towards convergence actually. Okay. Anyway, so this check for convergence, if it is converse, they take the converse solution and stop actually, and if it doesn't, then you just go there and then update the compute the sensitivity matrices recursively and then update the control history and go. Now, also remember a small comment out here that is for control to adjust, it all depends on this dyn actually. Okay. Because this algorithm, if you see the convergence check that you are doing here is dyn whether it has gone to 0 or not. Now remember, these are nonlinear problems that you may have multiple solutions and things like that. That means, if your guess happens to be good, okay, even though the trajectory need not be optimal from cost function point of view, you may actually get eluded that yn has gone to yn star and hence my solution is optimal actually. So, my suggestion for that is do not get eluded that way. You allow for at least one iteration forcefully. That means, do not bother about checking convergence from the very beginning, just allow one iteration. From the second iteration onwards, you can probably check actually. Okay, so that is what it is actually. All right. So, I have all told everything on the way, but let me summarize the reasons for computational efficiency, why it is computationally efficient. The very first thing is I told the costed variable becomes static. That means, only one time independent, that means constant costed vector is needed for the entire control history update basically. That is the primarily the major reason why it is computationally quite efficient. And then dimension of the costed vector is same as the dimension of the output vector, okay, which is typically much lesser than the number of states actually. Okay. Essentially, if this is lesser, then the dimension of the lambda also becomes lesser actually. It is directly, I mean it is same as the output vector dimension actually. And the costed vector is computed symbolically. Okay, costed vector, well, it's theoretically speaking, it is costed. Okay, costed vector at every iteration is computed symbolically, and then it leads to some sort of a closed form control history update actually. Okay, it does not lead to closed form control per se, closed form control history, but it leads to this closed form control history update. Okay, DUs you are able to kind of compute very fast actually. Okay. All right, the computation okay, involves largely the sensitivity matrices, which are also computed recursively. That is another reason why it is computationally efficient. And if necessary, as I told, concepts like iteration unfolding can be incorporated to save computational time even further actually. Okay, so these are the last issue is primarily an mechanization issue, but all other things, the first 5 issues, 5 points, are actually the algorithmic centric actually. This happens because of the algorithm really. Okay. And there are important extensions also we have proposed, and I will probably take you through some of these. And then extensions is first thing is there is a variation of this which talks about something called model predictive spread control. Okay. This is a kind of a version with control parameterization. That means, you parameterize the control variable. Okay, let me talk about that a little bit philosophically. Suppose u contains something like u1 and u2. So, what you do is ui, let us say you parameterize like a constant vector or something like a I t I or t go sort of thing. Initial guidance will do that. So, a I t plus something like b I. That means, with respect to time, what I am looking for is something like a okay, sorry for that. What I am looking for is with respect to time, I am looking for something like a straight line equation actually. Or you can think of b I 0, then this straight line passes through the origin, or probably you can think of a I 0, then it is just a constant thing and all that. Okay, so, but the constant itself is updated in a systematic manner using this philosophy and all that. So, that is model predictive spread control. So, what it does, it further improves the computational time, because instead of entire control history grid point by grid point, what you are doing here is updating the coefficients only. Okay, grid points are automatically taken care because of the polynomial fitting that we already have. So, essentially it further improves the computational time. And also it smoothes the control history by enforcement. So, remember the other one may or may not happen, because every grid point it is treated as some sort of independent control value basically. So, smoothness may happen, and it does happen in most of the cases, but theoretical guarantee comes when you have something like a polynomial fitting. So, no matter whatever a I and v I you take, this is essentially some sort of a what you see here is this is u I, okay, and this is t. Okay. So, this is guaranteed to be smooth actually. Okay. So, that is this part of it. We will see that I mean probably 1 or 2 classes down the line actually. Okay. And then there is another extension which is called generalized MPSP, very recent development around 2011-12 like that. So, what happens here is we started with something like a discrete time framework, and so essentially we have revisited the entire problem formulation, and we have proposed some sort of a equivalent development in continuous time framework also. That means, somebody, I mean, it is not necessarily that you have to start with discretization of the formulation and all that actually. You can carry on with the continuous time framework from beginning to end, but of course, for implementation sense you have to always do some discretization at the end actually. I will talk about these two methods in after one more class probably. Okay. We will see some of this generalization and things like that. Alright, so these are extension part of it. Now, coming back to some example problems and all. So, I thought instead of going through this typical textbook sort of small examples, we will rather go to a very practical example and see what the implications there actually. Okay. So, this essentially talks about re-entry guidance of a reusable launch vehicle. Okay. And as you know, this reusable launch vehicle is also a kind of draws a lot of attention world over, because essentially by repeated launch of the vehicle, okay, you are essentially aiming to bring down the cost of the launch of the satellite actually. Okay. So, that is what it happens, but it throws its own challenge and all that. So, how do you overcome that and all, we will see actually. Okay, so, this is a typical kind of trajectory and all that from beginning to end. The launch vehicle takes some sort of a vehicle at its top. Okay. On the way, the launch vehicle itself drops out, and after that this vehicle, okay, has to be recovered, and it has to essentially go to a runway, but also you can think about something like a splashdown in sea and things like that, but you can essentially run to some sort of a runway actually. Okay. So, this is the re-entry segment that you are interested in, and then we are talking about these numbers and all you can forget. These are I mean typical values and all, but it does not matter. It depends from vehicle to vehicle, varies from vehicle to vehicle like that actually. Okay. But essentially the approach is somewhat similar. It goes to somewhere, and then after some time, or it actually launches a satellite there, and then after launching the satellite it has to come down and recover itself. So, what you are interested in here in this particular problem is the re-entry segment. Okay, this re-entry segment is a very critical segment, because it several constraints acts on the vehicle actually. So, how do you do that? Okay. And remember this MPSP technique that we are talking here, there are certain kind of limitations as well, which we did not talk probably. The very first limitation is okay, but let me kind of go back to that and probably show some of that basically. Okay, so, the cost function that we have assumed, okay, conveniently rather, happens to be a function of control variable only. Okay. So, the boundary conditions are there, that means at t equal to tf there are certain objectives for the output and all that is there, but on the path actually where the cost function is not a function of the state, it is still a function of control only basically. The second thing is essentially what you are talking here is well, the control constraints and all that. So, those things are still not accounted for actually. Okay. So, essentially by using this necessary conditions here, what you are assuming is the control is actually unconstrained. Okay. Okay. So, these are the primarily two kind of limitations that acts on this algorithm. Okay. As of now, of course, I mean you can think of doing further research to kind of relax some of these conditions actually. Anyway, so this is what it is, and this is re-entry segment, and we are interested in something like the idea here is to develop advanced nonlinear and optimal guidance for an RLV, okay, in the descent phase with special emphasis on critical re-entry segment actually. So, what are the challenges here? Okay, the first challenge is path constraint, and path constraint there are several constraints, the structural load, thermal load, angle of attack boundary, there are primarily three things together. And then there is this and remember this angle of attack plays a very critical role because it essentially gives two things. One is controllability of the vehicle, and also very strongly coupled to the structural load actually. Structural load is a direct function of angle of attack really actually. Okay. So, this has to be kind of handled very carefully actually. Okay. So, there is a path constraint which essentially talks about structural load, thermal load, angle of attack boundary like that. And there is also a terminal constraint that ultimately at the end of the re-entry we want to go to some position and then in specific velocity vector sense also basically. Okay. So, that means the velocity magnitude as well as its direction needs to be in specific direction. So, that ultimately we can recover the vehicle and land the vehicle actually somewhere. Remember this RLV does not have any thrust, that means you get only one chance to land actually. Okay. You cannot keep on moving around an airport and try to find out and things like that. It just gets one chance, and then with that one chance we have to get it back actually. Okay. And then we also aim to generate some sort of optimal trajectory, and then obviously it has to have robustness with respect to uncertainties parameters. What we mean in parameters is essentially inertia and aerodynamic parameters. And typically they are not very accurate, they will have some 20-30% inaccuracy in aerodynamic parameter and some about 5-10% inaccuracy in inertia parameters like moment of inertia, mass and all that actually. So, the algorithm has to be robust to that actually. Okay. Then there is this real time computability issue, and obviously there is another issue of smoothness in the guidance command generation also. Why do you need smoothness? Because ultimately what you interpret as control variable in guidance loop happens to be nothing but the output, reference command input to the inner loop, okay, where it needs to be tracked perfectly actually, tracked as close as possible. So, that is where having a smooth history in the guidance command actually helps there basically. So, these are the things that you are looking for here. Okay, now, when you go back to this dynamics, I have taken this dynamics from this reference. Essentially, I think this book is available probably free download or something these days. I have seen soft copies actually, but anyway, so otherwise you can think of locating in some library and all that actually. Okay. So, anyway, so this is obvious. These three equations are essentially the radius from center of earth, and then there is this latitude and longitude actually. Okay. So, essentially it talks about spherical earth and rotating earth as well actually. It talks about everything, spherical, rotating earth. If you assume that, you talk about spherical trigonometry and all that way. And the coordinates, position coordinate that is defined is in terms of r, pi and theta, okay, altitude essentially, and this latitude and longitude actually. But this is kinematic component. What about dynamic component? Dynamic equations will contain v, gamma and psi, which v is the velocity magnitude, and gamma and psi are essentially the flight path angle and heading angle actually. So, if you see that, this equation has already become quite kind of a messy actually. Okay. So, first thing what it is formulated only with pitch plane maneuvers. That means, we thought okay, bank angle can be suppressed. In other words, bank angle, all that it assures is just moving the vehicle in the one single direction without changing the direction of the velocity vector sidewise actually. Okay, it just goes up and down vertical sort of thing. And also we neglected this earth rotation part of it actually. Okay. So, okay, it's a short duration mission. If it happens, the earth rotation doesn't matter that much. So, what happens there actually? Okay, so okay, with that results, these are the some re-entry conditions that you constraints that you think about. There are some of the values that we applied to the kind of problem, and then we thought, okay, what about getting the solution out of it actually? Okay. So, then I told this okay, this is a formulation in terms of really what is called as specific energy, and specific energy is nothing but this kinetic E is something like kinetic energy mgh plus half mv square divided by mg, okay, per unit weight actually. So, essentially it h plus v square by 2g sort of thing actually. Okay. So, this is if you know E, and then if you know V, the h is given actually that way. So, these three are linear dependent now basically. So, we talk about V and gamma essentially, and then control vector is alpha, and the output vector happens to be z sort of thing actually, whatever is there. Anyway, so this is the formulation that we followed, and also remember this is angle of attack is bounded between these two. So, we wanted a middle value as close to that as possible. So, with the cost function assumed was something like deviation minimization actually. So, part of that this part does deviation minimization, this part kind of assures normal load factor should be minimum, okay, and this essentially kind of guarantees smoothness actually in a way. Okay. So, what you did here is if you see this result, this is some sort of another method solution actually what you have in blue line here. Take that as initial guess actually, okay, and then run it through this algorithm, and then found out that okay, this problem can equivalently be solved using this trajectory rather what you see here in this colorful red line sort of thing. Okay. What is beauty here? This line compared to the blue one, this one is not only smoother, okay, which is much more smoother actually, and it also happens to be lying somewhere in the middle part, okay, whereas this blue line is actually touching to the upper side right here, which is not allowable actually. Okay. Anyway, so coming to the perturbation study and things like that, we have done some okay, some sort of perturbation study is using this randomly varying coefficients and all that. And essentially done some 480 simulations and all that, and some different middle points, initial points and things like that. Essentially you can see that the normal load, since it is slightly getting violated here, its value is 3g, but it is getting around 3.2g sort of thing. But the number of cases that got violated is also small actually. Okay. So, if in other words, if the structural limit becomes 3.2g instead of 3g, then it is within that. But even otherwise, the number of failures are very small actually, okay, and every time it happened to be in the middle of the boundaries basically for the alpha. Okay. They also remember the bound values themselves are a function of Mach number. So, they are not fixed numbers actually with respect to time. The Mach number is is velocity, vehicle velocity by sound velocity, is a dynamic variable. So, the bound itself, bound values itself change depending on the situation actually. So, that is why you can see bunch of bounds values here actually. Alright, and ultimately you see these points are meeting at the desired point. This altitude was desired to be something like 20 kilometers. So, it is all happening at the end, and velocity also desired value is meeting. You can see there is a flat line sort of thing. So, no matter what happens on the way, the boundary conditions are enforced as hard constraint. That is the reason why it happens this way actually. Now, what about the next formulation, which talks about both pitch plane and yaw plane maneuvers actually. That means alpha, angle of attack alpha as well as bank angle, both are control variables. Then what actually? Okay. Remember this part of the problem formulation. Okay. We didn't bother much for the position coordinates actually. Whatever position coordinates happens, but ultimately our path constraints and all has to be met. And ultimately, I want some sort of a position coordinate in terms of height and height only rather in a way. The latitude longitude was kind of ignored basically there. But anyway, coming to this one, because we have bank angle maneuvers as well, so we can think about doing that also. So, instead of E and gamma, which essentially talks about H as well, because entire formulation is based on E. So, instead of V, gamma, H only, what we talk here is phi theta also basically. Okay. So, that is what we are interested in here, and then all other things remain same actually. Okay. So, these are the terminal coordinates what I am talking about here. So, what you did here is, if you, there is some little bit interesting thing out here. What you can see here is this variables you want to control, but they it's not a direct function of sigma basically. So, if you consider sigma as a control variable, then you have a problem here of controllability starts coming and all that. So, what we thought is, okay, we will consider psi as some sort of artificial control variable here, and once we get a psi trajectory, then we can think about going to psi dot equation and compute sigma, because psi dot is a strong function of sigma here. You can compute, I mean, once you have a psi trajectory, go to this equation and compute sigma based on dynamic inversion actually. So, that is what we have done there, and we can, what is happening here. Okay, so, that is what is done here, and this is the intermediate control for bank angle profile sort of thing actually. Okay. Then also it was done, some normalization was done, because remember V happens to be a very high large quantity and gamma these are angles. So, in radians which are small quantities like that, we introduced this this normalization thing and then operated based on normalized dynamics actually. And as I told, J consists of 3 parts, and then J1, J2, J3. J1 contains this normal load factor, and remember it operates on some factor here, which is an exponential function of the previous normal load at that particular point actually, grid point. That means, if there is the iteration sense, if the previous value has taken it towards the boundary, then the weighting function is increased. That means, the update happens should happen in the negative, I mean in the other direction actually. Okay, so that is the whole idea here. Okay, so that is the how to address this normal load bound sort of thing. And then this J2 happens to have this control deviation minimization actually. And remember, when you talk about deviation minimization, if you talk about the reference profile as something like 0, then you are talking about the control minimization directly actually. Okay. So, J1 is done to take care of the normal load constraint in a soft constraint way, and then J2 is done to take care of the alpha boundaries and sigma boundaries, things like that. And then, okay, these are all mentioned here. Okay. So, essentially this fellow is effective, okay, only if the value is close to the bound, otherwise it is a very small value anyway actually. Okay. But when it is close to the bound, it is increased exponentially. So, suddenly this shows a source is power actually sort of thing. Okay. So, this is what you see here J2, okay, and this is what is done for smoothness actually. Smoothness means, remember, the derivative is small, that means the difference between these two should be small. But once you directly formulate that, the cost function becomes some sort of a complex function. I mean, the algebra becomes messy and things like that. So, what he thought is, okay, instead of getting this deviation minimum, what about making this deviation minimum and that deviation minimum? What is this? This is actually the previous value of two neighboring node points, previous value of the control. This is what you want, the correct value of the control, k minus 1 and uk, uk minus 1 and uk. They happen to be the current values of control is uk, this is what you want after update, and this is what you want after the update at k minus 1. But these things are already available, these are numbers actually. Okay. But if you want to play around directly, then the cost function becomes a kind of an involved function. So, the algebra is messy. What you thought is, okay, we can get away from that by just having this innovative formulation where you talk about, okay, this minimize the difference between uk and uk minus 1, whatever it is, it can be minimized by minimizing the difference between uk and ukp, so the previous value of the control at the same grid point, as well as the difference between uk and uk minus 1p. So, if I minimize this and minimize that, and obviously this has to be, this will be minimized actually in a way. So, that is the philosophy we have followed here, okay, and telling that, okay, I mean this is anyway taken care, because we want deviation minimization here. Okay. When you do that, that is already taken care. What you do is, okay, we just need to do this minimization also actually. This is what is given here, okay, for the smoothness part of it. Alright. So, these are all explained here, what I have told already here, and then essentially the cost function is ready, your algorithm is ready, these are some of the results actually. So, what you see is some 8 cases we have plotted. So, you can see that for each of the cases, all of the arguments that I told you before remains valid, and ultimately all of the cases different color coding and line coding you can see. And remember, if you are concentrating on that particular line here for the control segment control history, then you should also concentrate on that particular line for the maximum bound and minimum bound, okay, because everything happens to be time varying sort of thing actually. Okay. Essentially, if you concentrate this line, then your this is the upper bound and that's the lower bound, the control history is like that way, what the solution what you got actually, like that. So, essentially you can observe that all the alpha solutions, angle of attack solutions happens to be smooth as well as they happens to be somewhat at the middle of the both the bounds actually. Okay. Now, what happens in the sigma part of it, the bank angle, we took some plus or minus 30 degree, and in fact it can be taken much more than 30 degree, because in case it is in a kind of an unmanned mission basically. Okay. If you do not have human sitting there, probably the vehicle can turn little more, can roll little more actually. So, anyway, so coming back, we put some 30 degree plus or minus 30 degree bounds for our particular experiment. So, we started with different initial conditions and all. Ultimately, you can see that finally, it is taking there, but also remember the final bank angle what you are looking for is happening to be 0 actually, which is also neat. Because ultimately, at the end of the re-entry, you want to be some sort of a 0 sigma attitude sort of thing actually. Okay. So, these are some of the comments that I already told. These are all smooth profiles and trim bounds are not violated here. And you can also see that the final conditions here are met in a very tight condition sense. You can see no matter whatever is the initial condition, ultimately they end up at the same value. That is why the final boundary condition is enforced as some sort of a hard constraint actually. Okay. So, these are the powerful things that you talk about when you use this optimal control based methods and approaches, all that actually. And you can also plot these other different things, this normal load and this kind of dynamic pressure values and all that actually. You can see that all these, this is strictly below 3G, and then this is this constraint is met, okay. And then you can see this heat flux is also met actually. Okay, dynamic pressure, this is the value for dynamic, this is the dynamic pressure, okay. It has to, the bound is about 25 kilopascal, but what you are getting here is 14-15 kilopascal actually. Okay. Heat flux is actually 60 watt per centimeter square, but what you are getting is way below basically. But that again depends on the mission and all that actually. So, if you go to higher and higher altitude and then try to come back, your energy will be high and hence other things will come up actually. This particular experiment that you have done, it turns out that heat flux is not a major constraint actually. Okay. So, in conclusion for this lecture, what it turns out that MPSV technique is a very promising technique for optimal missile guidance in particular, but trajectory optimization in general. So, what it does is trajectory optimization philosophy is brought into the guidance design. That's more important actually. Okay. So, it can be used in missile guidance, it can be used in any UAV guidance for example, any autonomous guidance problem, autonomous vehicle guidance problem that you talk about. And you formulate it based on this particular formulation, if it is amenable to, okay, then you can think about using this, and it will essentially lead to this optimal trajectories and optimal guidance, all that. Various challenging, we have solved various challenging strategic and tactical missile guidance problems that I will take you through in the next class, next lecture actually, some of these problems, okay, and still being solved actually. Many things you can think about posing the problem in a good way, then try to extract the benefit of this method actually. It has also been successfully demonstrated for re-entry guidance of a reusable launch vehicle that I have just taken you through. And then there are some extensions like MPSC and all that with control parameterization. There is additional desirable characters like smoothness and things like faster computation and all that actually. So, it is now slowly getting worldwide acceptance as well. I have seen many people kind of liking this, referring this, using in their problem and things like that. So, I encourage all of you to kind of put your hands on this, and the algorithm is rather simple to code and experiment also basically. Alright, so with that probably I will list out some references. Okay, these are the references that you can think about. This is the first one, as I told, the last one is the very first one. But I have taken this RLB problem from these two references. One is already there, And the other one in the conference version is there, and the journal version we are trying to submit as soon as possible actually. So with that I will stop this lecture. Thank you.